Hi, class. Good afternoon. Today's lecture will be continuing with computational arithmetics, if you will. Right. So let me start by we should revisit something from last time because I messed up an example on my little whiteboard, and the computation wasn't quite right, and also I didn't cover exactly what I want about this example. Namely, I didn't go to the extended Euclidean algorithm. So let me start with that. So here is the flash of the Euclid's algorithm for finding GCDs of two integers, right? So it's a recursive algorithm. If B divides A, then you just return B. That's your base case. And otherwise, you call recursively shifting. So B is the smaller of the two is your new A, is your new larger of the two, and the new smaller element is computed as A mod B. Okay, and we said that extended Euclidean algorithm not only solves, gives you the GCD of two integers, but also gives you these linear coefficients S and T, such that you can. It is true that the GCD is a linear function of A and B, and S and T are the linear coefficients. Okay. Okay. So I already see I messed up animations on this. So ignore these red boxes. But disregard the red boxes for now. This will be the final conclusion from the slide. So here is the Euclid's recursive algorithm in a nutshell, right? GCD on AB. If B divides A, then you return B. That's the base case. And if this is not true, then you recursively call GCD on modified inverse. Okay, so let's see how this works. This was the example I messed up last time. 259 and 77 are the first A and B, okay, that we're calling with. Okay, so what do we do? So first, does 77 divide 259? And, I can tell you no. And so you're going to call GCD recursively on new. This will be your A1. So I'm indexing AI, BI is the A and B of the ith recursive call. So I'm calling the first call the number 0, and then the first recursive call would be 1. So these guys will be A1, B1 in the next call. Okay, so what are they? So we have to just compute A mod B. Okay, so what's 259 mod 77? It's 28. And the reason why it's 28 is because the following equation holds, right? I subtract multiples of 77 from 259 until I get something that is in the range, right, between 0 and 76. So this is a remainder. So it turns out I can fit 3 multiples of 77 into 259, and this is the equation. All right, so I know this value in the next recursive call. So in the first recursive call, rather, A1 is the previous B, so B0. So this 77 just got copied here. And B, which is B1, because it's B of the first recursive call, is 28 because 28 is the A mod B. Okay. Okay, so that's the next recursive call. So what do we do? Well, first of all, 28 does not divide 77. So I think that you can see. And so we are not in the base case, so we're here. So we have to compute A mod B. Well, this is A, this is B, and this is where I made a mistake. I computed this at 11, last time, right? All right. So this is 21 because if I take multiples of 28 out of 77, and I fit 2 of these, right? This is 56, and 77 minus 56 is 21. Okay, so again, in the next recursive call, the A value is the previous B. So this guy got copied here. And the B value is A mod B of the previous A and B, right? So it's going to be 21. Okay, so let's recurse, right? I have to, again, 21 does not divide 28, so I'm not in the base case yet. So I have to compute 28 mod 21. Well, that's simple, right? It's 7. So the next recursive, again, the new A is the old B. It's right here, right? That fact. And the new B is 28 mod 21. 7. And now we're hitting the base case because 7 divides 21. So 7 is the answer. And the answer just percolates back through all these recursive call, right? From the next recursive call to the previous one, right? So the answer is 7. And when you compute this, it's always a good idea to check. So check that 77 indeed prime factorization of it is 7 times 11. And 259 divides by 7 is divisible by 7. And well, 37, it's a prime, but what you care about is that it's 11 is not its multiple. Okay, good. So we see how algorithm works, and now was the time when I was supposed to put these red frames, because 2 points about it. The B's are the only trace of this algorithm that matters, because you see the new A is the previous B. So this is not really that interesting information. It's just a copy of this stuff. And this guy is basically lost at the very first call, okay? So kind of this is the important trace. And look, that the way we got there was because of these equations, right? At every point, we have we have represented the next B as the previous A minus some multiple of previous B. And the next B is previous A minus some multiple of previous B's. Okay. So first of all, if you flatten this previous A is really a B 2 steps back. So this guy is a linear combination of these two. Is this times plus some multiple of this. It's a negative multiple, but it doesn't matter, right? It's some integer times 77 is this. So you actually have a linear equation, and this is this equation that represents 28 as some linear combination of these inputs, 25 and 67. This is the original A and B. Now, the next recursion says that the next guy is representable as a linear combination of these two. It's syntactically these two, this is A and B, but this guy is that one copy. So it's really the previous two B's. And this is this linear relation. And again, the next guy, next B, is a linear relation. It can be represented as a linear relation on the previous two B's. That's this relation, right? So if you recover these linear relations, you can represent the final guy as a linear representation of the linear function of the inputs. And that's what this asks for, right? The final answer, 7, is there is some coefficient s and a coefficient t, such that if you take this s times and you add this t times, you're getting 7. Now, one of these has to be negative, but that, whatever, right? So, yeah. So, taking t times might mean taking negative t times, right? But, okay. So let's look how this would, you know what? And I don't like my next slide. So instead of doing it on the oh, I see, because I disconnected my little camera here. Back. Okay, and let's go to the little camera here. It will get into focus when I start writing. So I have again GCD of AB is if B divides A, then B, else GCD of B and A mod B. So that's the whole recursive code. Let me try to focus now. Okay, so hopefully that's better. And let's I will copy this run on. So my initial inputs were 259 and 77. Okay, and my goal is to find S and T such that S times 259 plus T times 77 is equal to GCD of 259, 77, which in this case turned out to be 7. Okay, so how did this algorithm go? So my initial values were 259, 77. Okay, and I had this linear relation that the next B, so to speak, was a linear relation of these two, and you know, I will represent it for the reasons that will become apparent later in this way. Okay, so this so far this is an annoying rewrite, but it will be actually a useful one. So my next parameters are 77 and 28, right? Because I compute A mod B. This is A mod B, right? So okay, let's recall that the end result of this was that 28 is the 259 mod 77. Okay, so this is my next call, 77, 28. Now the relation I found between them was that 21 it was 77 minus 228, and I will represent it like this, minus 2 times 28. Okay, and what I wanted on the level of this algorithm was that I wanted to compute 77 mod 28, and this was the result of this computation. Okay, so this, you know, what the Euclidean algorithm does is to try to compute this, and this is just the technique that it uses, right? So the next call was therefore I copied the B, and this is my new B. Okay, then what I want to compute is 28 mod 21, which is 7, and the reason why is that 7 is 28 minus 21, which I will represent as, sorry. You know, when you see that I'm making an arithmetic mistake, you should unmute yourself and say so.
Did you mean to say 1 multiplied by 77? Because like
yeah,
I was...
exactly. Very good. So it's 1 times 77 plus minus 2 times 28. Yes. Okay.
Sorry, one quick question. Are the solutions for the exam, the second exam, online yet?
No, and I will not post them in that fashion because I don't want people to, you know, distribute these solutions. But I will post solutions essentially on Piazza.
Piazza? Okay.
But in a form that is not so easy to copy. Haha. All right. So 7 is 28 minus 21, which is like this. Okay. And the next call, A3B3, is I copied the B, and this is my new B, right? And now I'm done, right? Because 7 divides 21. Okay, so the answer it was 7 to the GCD question, right? So hence I got that. But okay, but now I want to compute. My goal is to find these two coefficients. And look, the coefficients I was talking about are exactly these. Here is the coefficients that represent, look at the sequence of B's, okay, is this sequence. Okay, the next one is a linear combination. Okay, you know what? And I will copy 259 as some sort of B minus 1 here. So 21 is a linear combination of these two by this equation. And 28, sorry. And 21 is the linear combination of the previous two. And 7 is the linear combination of the previous two. So let's now go backwards to represent this. I already have my end goal, 7, as a linear combination of these two. How about I want to make it a linear combination of these two? Well, look, I have this equation where basically it's some sort of S0. Oh, okay, well, I guess I shouldn't call it S0. Okay, whatever, I will. You know what? Okay, I guess. No, you know what? Let me call it A times 28 plus B times 21. So that's this equation. And this equation is that 21 is C times 77 plus D times 28. Okay, this equation. So now 7 is A times 28 plus B times 21. But 21 can be rewritten as this thing. So I do C times 77 plus D times 28. And now I just group the elements. So I have B times C times 77 plus A plus BD times 28. So I did represent this guy as a linear combination of these two. Okay, so I'm almost there, right? Because now, where am I here? Sorry. Okay. Okay, because now I have a combination that describes 7 as a linear combination of these two. And where do I see them? Okay, I have 28 is a linear combination of these two. So all I need is to basically use 28 here and to put it here. And what I did before was to put 21 into here. Okay, so let me do that. So 77 was, I already knew that it's BC 77 plus A plus BD 28. But I knew also that 28 is some other coefficients, call them A, B, C, D, E 259 plus F 77. And now, so I put the 21 here. So therefore I can rewrite 7 as BC 77 plus A plus BD E 259 plus F 77, right? So, okay, so finally what I get? Some unpleasant thing, A plus BD times E times 259 plus BC plus F A plus BD times 77. You know, you definitely don't need to memorize or anything, you know, what these things are, right? That's not the point. The point is that that 7 is representable as some linear combination of 259 and 77. This is the S, and this is the T that I was searching for, right? And the way to compute these is to go back through this code. And you know, you can, of course, if you are curious, if you somewhat ambitious, you can write this in code, and it's not going to be that complex. The code that not only passes the final solution, but also passes on the way on the return. It returns these coefficients, ST, these local coefficients, so to speak, and then given some function of A and B, which was already basically computed at this moment, you combine it to create the coefficients on the way out. Okay. Okay, so that's all I want to. I mean, that's what I wanted to tell you about this. That these things can be computed, and they basically follow from the Euclidean algorithm. Okay, so we are back at. No, we are not.
How do you determine the values of A, B, C, and D, and E and F? Was it because they're already given and previously, like you could figure out the appropriate linear combination?
No, yeah, because they're all here, right? Like,
okay.
So this is, you know, I guess these two are E and F, are these two, right? And so on and so forth. And C and D are here. This is the C and D, and right?
Okay, I see.
Yeah. Yeah. Okay. So so let me go to the back to the presentation. I have to get a sense of hold on, how do I do this? I'm a little lost. Okay, no, I think I'm correctly here. Okay, so I hope you see my slides now, and the whole, you know, I have this sort of animated here, but I think it's worse. But anyway, there's another work, you know, here on the slide is another way to work out this example numerically, so you know what these SFT actually are for this particular case. I think it's just less good as a general explanation of what's going on. Okay, but if you want to test what happened in this particular example, you can, and that's the slide. Okay, so now why is that important? Because this extended Euclidean algorithm allows you to compute multiplicative inverses in a modular arithmetics. So if you compute RSA private key, that's the algorithm you will use, or in many there's many other applications in public key crypto. Okay, so okay, so if you remember, we call if you have two integers A and B, which are residues mod n, such that this equation holds, their product is the 1 mod n. Okay, then this integer B can be called multiplicative inverse of A and could be denoted this way. Okay, again, this thing does not exist over integers, right? There is no inverse of 2 over integers. It's a 1/2, but that's irrational. It's outside of integers. But in modular arithmetics, these things exist. And on the homework, you will see that they exist if you do modular 7. But if you do modular 8, actually, for a lot of things, they don't exist. And that's because 8 is not a prime. Okay. So that homework exercise, you know, that was like sort of one of the conclusions of it. Okay, so here is the multiplication mod 5, right? And you see that things have inverses, right? So the inverse of 1 is 1, but the inverse of 2 is 3, right? Because 2 times 3 is 1 mod 5. And the inverse of 4 is 4. So the place where the number that multiplied by 4 gives you 1 is 4 itself, because 4 times 4 is 1 mod 5. Okay, so these are the inverses. And I will skip this. This has no inverses, so you can look at this later. But I mean, that was the homework exercise to basically do this mod 8. So these things don't exist. Why extended Euclidean algorithm actually allows you to compute them. So of course, for small moduli, like the ones you had in the homework, you do it by hand, and it's fine. But for a large n, and for and the modulus is a 100-digit number, it's not too clear how this can be computed fast. But here's the observation that if A is that A has a multiplicative inverse mod n, if A is relatively prime to n. So you might have observed this doing modular math mod 8, that the only things that have modular inverses were 1, 3, 5, and 7. All the numbers which are not coprime with the modulus, right? So which were even, because 8 is just the power of 2, right? So the only factor is 2, really. Did not have multiplicative inverses mod n. Okay, so which is one of the reasons why we use primes in a lot of crypto systems. It's actually the extended Euclidean algorithm could work as a proof for this, because it explicitly allows you to compute this inverse if A is coprime with n. Okay, so I'll show this on the next slide. So suppose n and x are relatively prime. Okay, so GCD of n and x is 1, which means that the Euclidean algorithm on n and x gives 1 eventually, right? Like the recursion ends and 1 is an answer. Then by extended Euclidean algorithm, we know that these integers s and t exists, and extended Euclidean algorithm computes them, which show that the GCD of n and x is a linear combination of n and x, and GCD of n and x, by assumption, is 1. So these coefficients that an extended Euclidean algorithm outputs in the case that x and the modulus n are relatively prime is 1, right? So these coefficients will satisfy this equation. So here is the kind of nice thing. This coefficient actually is the multiplicative inverse of x mod n. Why that is? Okay, so you can see this in general, but first look at the example. So let's say we want to know what's the multiplicative of inverse of 54 mod 79. Okay, 79 is actually a prime, so the GCD will show that they are coprime. And the extended Euclidean algorithm will actually find these coefficients, and they turn out to be 13 and minus 19. Okay, so they're bound by this equation. And so the answer, okay, sorry, messed up animation again, does not matter. The answer is this coefficient, right? So the multiplicative inverse is the coefficient in this linear equation next to x. So the multiplicative inverse is x here is 54, is minus 19. So that's the multiplicative inverse. And because we are doing computation mod 79, right? The question is find multiplicative inverse of 54 mod 79. It's better to represent minus 19 and as a 60, right? Because in a modular arithmetic mod 79, it's just a better thing to represent numbers as, well, remainders of, right, between 0 and 78. So minus 19 is really 60. And now, why is this why is this thing true? Okay, so this arrow really should be pointing here because I'm explaining this general fact. So look, x minus 1, x inverse is b, is some number b such that x times b is 1 mod n. And now that last equation, right, holds if and only if xb can be represented as some multiple of a modulus plus 1, right? So only then xb is 1 mod n. There is some number of n's you subtract here and you get a 1. Well, this is this equation. And if you just now, this equation is the same as this one, right? So b is t and m is minus s. So this equation is basically this one, just change of variables, change of terms, right? Which means this one, which means this one. So that's why we can conclude this from here. Okay. Any questions on this part?
So is this used to create that table as well? Or this is just to find, just to like express it in terms of a linear combination?
You know, I don't know what you're asking.
Oh, sorry. Is this like is this used to create that table of elements of like, let's say that table from the previous slide? Yeah.
No, because
No,
for
it's not.
small n's, you don't need to do this.
Okay, so this is just a linear combination, right?
Wait, okay. The homework has small numbers, so you don't need to run this algorithm. So yes, this algorithm allows you to compute multiplicative inverses for large numbers, for any numbers, and any size, because a good thing about Euclidean algorithms is they're so fast, right? As I was arguing last lecture, already hand waving that argument. So you can run this recursive algorithm, and it will compute these coefficients on the way back, and it will give you the multiplicative inverse. And that's how inverses are actually computed in practical implementations. That has nothing to do with the homework, because the homework has small numbers and you just compute them by hand. Okay, this will have something to do with the next homework, but not this one.
Okay.
Okay. Yeah. Somebody asked if this is a linear equation. I mean, yes. I'm saying it right here that it is. All right. Okay. I will go on with the. I'll move on to the to another topic. Number representations. So representing numbers in different bases. Okay. So here we have. I mean, all of you have seen this. That right? What is the base 10 representation that we all use? Right, the decimal system of the. Well, I don't know where it started. I know that the Europeans took it from the Arabs, but I don't know whether Arabs took it from whom actually, or just came up with this, right? Each place, yeah, and what was the, Romans obviously had the, okay, not obviously, for Europeans, is we know that the Romans had the other numerical system. So what was the numerical system used by the Chinese? Did they have decimal system from the very early, or not? And what about? So assume Japan and Korea just take stuff from China, and And what about other cultures? I have no idea, right? So you post some link on Piazza because I'm curious. Of course, Wikipedia will talk about this too. All right. Each place represents a power of 10. So a number like this, right, in a decimal system is just, you read it from the back, and you these are basically coefficients next to consecutive powers of 10, right? And the coefficients are integers in Z10, right? So between 0 and 9. So that the maximum value of here will never hit this. And the maximum value here will never hit this, right? Because the maximum power here is 9 times 10 and 9 times 1. And this is never 100, right? But it's exactly 1 minus 100. Okay. So that's how you read. Well, computer science, right? Like we often use the binary. And so in the binary notation, every digit, there's only 2 possible digits, right? So the digits are in Z2, which is just 0 and 1. And the way you read them is these are coefficients next to consecutive powers of 2, because now 2 is the base. But it will again hold that the largest number represented by this is exactly 1 less the minimal number represented by the next power, right? So that's an invariant in any base whatever system, right? So it was true for base 10 and it's also true for base 2. So here's the general thing that we can use any base to represent integers, and the digits have to be in ZB, right? So residues mod B. So for example, base 7, the digits will be from 0 to 6. And if you represent a number base 7, and this is the notation, an integer in round brackets with a subscript denoting the base. Okay, so here I didn't use this notation, right? I didn't say that this is to be read in decimal. That's because I don't have to, right? Like nobody who writes decimal numbers constantly writes, oh, I mean decimals, I mean decimals. Now in here, maybe I should have written that I don't mean 1011. I actually mean here a bit string. I mean this to be a base 2 integer, writing of the integer, right? So to disambiguate, I would put brackets with a little 2. Okay, so base 7, these are the valid digits, base 7, right? And how would I read off what this number represents if I want to translate this into decimals? Then, okay, I take the consecutive powers of 7 and treat these as coefficients. And so this will be 2 times 7 to 0, 1, 7, 1, 6, 7, right? Then I compute what these powers are. And I have to remember that anything to the 0 is 1. Anything to 1 is that thing. And then the next powers I hopefully can compute. And I do the arithmetics, right? So base 10, this number would be represented as 303. And you might notice that in base 7, this number looked bigger than base 10. And is that a coincidence, right? Like basically, no. It would always be that way. Okay. Okay, although the exact notion of like what does it mean bigger is not so clear. Okay, so but typically the length of the description. Okay, so I can tell you that, right? Like the length of the description of a number base b, if base b is smaller than 10, then if I want to render this number not in decimals, I will definitely not expand it. it might reduce. It might, here it didn't reduce in size. I needed 3 digits here, and I have 3 digits here. But it will only decrease, never expand, if I go from smaller base to a larger base, right? If you cross multiply this, you know, you will have 8 plus 2 plus 1, so that's 11. So in decimals, you needed 2 digits, while in binary, you needed 4. Okay. Generally, it is true that for any base which is non-trivial, so greater than 1, it's non-unary, any integer is uniquely expressed as in base b. And why? Because for every integer a, there is a unique sequence of a's such that this is true. And moreover, the leading number is non-zero. Of course, I could expand this further down with like higher and higher power of b if my coefficients were 0, right? But I don't want to do that. I want like to cut it with the last non-zero coefficient and stop right there, okay? And moreover, each of these coefficients are in this range. This green sequence of AIs is unique for every n and for every b. And this sequence is the representation of n base b. Okay, so let's convert to the decimal some numbers, right? So 452 base 6, I envelop, right? So this is a 6 to the 0, which is hidden because it's a 1, and this is 6 to the 1, which is just 6, and then I just multiply to get the number. Here, okay, I actually put explicitly these powers of 2 and put in these coefficients in here. You can check that I did it correctly, right? So basically the 0 part I can ignore, and I only care about the non-zero powers, right, of 2. I mean, powers of 2 where there is a 1 in the corresponding digit. But, you know, it's always better to kind of do it slowly, because if you don't, you might mess this up and you might basically skip a power of 2. So even though it's simple, when you're asked to do this, like, it's better to, well, just do it by the book. Be careful not to jump some power, you know, and then compute. And okay, and base 9, you know, it's the same story, right? I just take base 9 stuff. So 9 to the 0, 9 to the 1, 9 to the 2. I interpret these digits as the coefficients, and I compute. Okay, now we can have bases that are higher than 10. The problem is that we don't know how to designate those digits, right? Because if we designate a digit with a 11, then it's not clear how to read, because is 11 a digit or is 2 digits, 1 and 1? Okay, so that's why we use letters of the alphabet to denote higher bases. And a common one used in computer science is a hex, hexadecimal, right? So base 16. So how many digits after 9 I need? This is 10, 11, 12, 13, 14, 15. I need 6 more letters. And so, for example, number 6D in hex base, right, is, okay, these are coefficient next to 16 to the 0 power, that's this one, and 16 to the 1 power, that's this one. And the letter is read as just a symbol designating, that designates essentially C designates 13, right? Because it's 10, 11, 12, and I may, no, sorry, and D is 13, right? D is 13. Good. So then I compute this, and it's 109. And now notice that if when I went from the high base to the low base of 10, my representation actually increased. I needed more digits. Again, it's not always going to be the case that it is expanding, but it's definitely not increasing, and on average expanding. So here is E1F base 16, right? I write consecutive powers of 16. I interpret these as E as 14, F as 15, and then do it slowly, do it by the books, because the common mistake is to think that the maximum letter corresponds to 16. Right, but that's not the case. Okay, so just be a little careful in these. And okay, and again in decimal you see that I need more digits to write this. So this is basically the way you if I give you the green sequence AK to A0, which are the digits base B, then of course you can compute what the integer that corresponds to in decimals. You just evaluate this expression. Everything we did was a case of that. What about the other way? You start with n, and you're told what the base is, and now find these coefficients. In other words, find the base B representation of n. Okay, so that's our next question. What is somebody is asking, yeah, the coefficients AIs are strictly less than B, right? The digits have to be strictly less than the base, right? So the digits in a decimal base are strictly less than 10. Digits in binary are strictly less than 2, and so forth. Okay, so representation of n base B, it's a very simple recursive algorithm. Hello and shout out to recursion again, right? So second time, because Euclidean is recursive as well, and multiplicative inverses therefore are recursively computed. So representation of n base B is a sequence of digits that can be computed this way. The last one is simply n mod B. Okay, so the last digits I can compute fast. The other digits I can compute recursively if I change n to n div B, which, by the way, I effectively do this when I compute this, right? So this is the common way of computing mod is to first compute the div and then do the linear equation, and you get the mod function. And okay, so very simple recursion. And when do we end? Where n is smaller than b. Then we don't recurse any further. We just output n. Okay, right? If our integer is already smaller than the base, then we don't do anything. We just, that's the integer. That's the base b representation of the same integer. So here is that code executed. So I want to know what's 735 base 5. Well, the last digit is easy. It's a 0, right? Because the number is divisible by 5, because 735 mod 5 is 0. Okay, so then I do modular integer division, and it's 147. So then 147 mod 5, so, and then I run recursively, which means what? I spit out the last digits in this way, so it's going to be 147 mod 5, which is 2. Next digit will be 2, and then I run recursively on 147 div 5. So I run it recursively on 29. So I do. Okay, and in that recursive call, what we'll do, well, first of all, I have to compute 29 mod 5. That will be the next digit. It's 4. And then I do a recursive call. So I do, what's the 29 div 5? It's 5. So that's my next recursive call. And well, 5 is not exactly the base case yet. It's not smaller than the base because the base is 5. So so I still not in a base case. I have to run the recursive case. So I output 5 mod 5, which is a 0. So the next digit is a 0. Then I finally get to the base case because the next call will be on 5 div 5. But 5 div 5 is a 1. So the next execution will be base B representation of 1 mod 5. But that's immediate, right? It's 1 because it's smaller. That's finally hit the base case. 1 is smaller than 5. So the last digit is 1. And now I read off these numbers backward, right? Because I accumulated them from the right to the left. So I got the least significant digit first, then the next one, then the next one, and the highest significant digit at the end. Okay, so this is the number, and of course, you should verify this when you do this. So I do have the verification on the slide, right? The zeros power I ignored. The first power is 2, the second power is 4, the third power is silent, the fourth power is 1. The rest is arithmetics, right? I compute these, and I compute these, and I compute these, right? And it is 735. Okay, so always go back. I mean, you know, it's nice you do this, but you have to go back and verify. I mean, otherwise, I don't think you have any sense of whether you have computed this on paper correctly. So why does this work? Okay, so here it is, the algorithm again. The base case is like this, and otherwise we just do the recursive call of n div b, and to spit out the last digits as n mod b. Okay, so here it's this case in a nutshell, right? As usual with recursive procedures, very small and powerful. What's so funny? It's like some movie or something. The mighty something, something small, but I forgot what that was. All right. Okay. So here's an argument why this is correct. It's going to be a recursive algorithm, small but mighty. Okay, great. Thank you. A proof of correctness. A base case. So it is a recursive proof, right? Like it is a recursive algorithm. So we go by structural recursion, right? First of all, does it return the correct value in the base case? Well, yes. If n is smaller than the base, then n base b is the same as n, right? You can compute this base b, and you will see that this is just n times b to the 0, which is n. Okay, so what about the recursive case? Well, so that's the induction step in the proof, right? That if it computes correctly on smaller numbers, then it will compute correctly. It's technically a strong induction. So let's take we want to argue that it computes correctly on some n which does not hit the base case, so greater than b. All right, what will it compute? It will take n prime, which is the parameter that will pass to the recursive call, and then it will compute the last digit, a0, as n mod b. Now, because, I mean, this means this, right? Because that's what div and mod mean. That if I do integer division of n mod divided b, this division times b plus the remainder, which is n mod b, gives me the n back. Okay. Now, let these digits be spit out by the recursive call. Okay, so denote them in this way. Okay, it's a1, the next digit, and all these remaining ones, right? Now, by the so you know that the full, if AK to A1 is the output of this call, and this you denote as A0, so the whole algorithm is going to return this string, okay, as the base B representation of n. Now, by inductive assumption, by inductive hypothesis, right, you assume that this call was correct because it's on a smaller number, right? You have reduced the size. So you assume it's correct. What does it mean? This means that this thing is a correct representation of base B of n prime. So it means this, okay, right? If I read off what this representation, I get n prime, base B with the consecutive powers of B, I get n prime. And now let's put this equation and this equation together and see, okay, n is like that, and n prime is like that. So I stick this inside of n prime, I get this. And now you can see, okay, what does this B multiplication do? It just gives a little kick to all these powers of B, right? So this becomes B to the K, everybody gets incremented, and this guy gets B to the 1, okay? And there is an A0 hanging, and that's basically end of proof that that AK to A0 is a correct base B representation of n. Okay, so I mean, if you stare at the what is base B represent, how do you? If you stare at this equation, then you will see the reduction. I mean, the recursion right from there. Okay, that doesn't matter. Okay. Here's you don't always have to do this. So okay, so now you know that okay, I can go from arbitrary base to decimals, and I can go from decimals to an arbitrary base. So if I give you something base 7, you can and says you what is the same thing base 8, you can take base 7 thing to decimals by the first bunch of slides, and then by the recursive algorithm take it base 7, or I forgot what my example already said, right? But there are sometimes shortcuts. And here's the important shortcut. If you have two bases which are powers of each other, then you don't have to do this laborious conversion. The conversion is going to be immediate. Basically, n digits of base B will immediately translate into a single digit base B prime. And the example that we particularly care for here is going between hex and binary. Because hex is base 16, binary base 2, and they're bound by this. And that means that 4 bits, 4 base 2 digits, correspond to a single hex digit, right? Which we say here. And so, and here's, and you can just write a translation table, all the hex numbers from 0 to F, all 16 of them. And here's the representation in binary. Okay. And so, you know, it's just a map between binary strings and hex strings. Here's how you could use them. So how you can use this map. So say, okay, you have a binary bit string, and you're asked, what's the hex representation of it? You don't have to go represent this in decimal and then laboriously represent decimal into hex. You can go directly, just split it into groups of 4, because as I say, a group of 4 tuple of base 2 digits correspond to a single hex digit. So group them in a group of 4. This guy is not a group of 4. It's the last guy, right? You don't have a guarantee that a bit string is always a multiple of 4, right? But no matter, it will, you can still, so always group them from right to left. Okay.
Can you add a 0, a leading 0 in front of the 1?
Oh, you can always have a leading 0. Yeah. Yeah. Okay. So right. So you put a leading 0, and now just read off these tuples of digits from the table, right? So 1001 is a 9 in hex. This is a 3, but this is a plus 4 plus 1, so it's the 13, and it's a D. And 4 is, and this is just 4. Okay. And here's your answer. So this is this bit string in hex. And you can therefore see, why people like to specify stuff in hex, right? Okay. Okay. Somebody sent some sort of stuff on hex to binary conversion. You might want to post it on Piazza too, because the chat tends to vanish after the lecture. Okay. Okay. So another question: how long the representation is when you go from base to base? So, what's the largest number that base 8 that has 5 digits? Okay. So it's 8 to the 5 minus 1, and the reason is that if you look at the possible base 8 digits, the largest is 7. So the largest number that is representable as with using 5 base 8 digits is this number. And so this, what is that? Well, I just evaluate. It's consecutive powers of 8 multiplied by 7. And you've seen this. This is a sum of geometric series, because you have powers of some base, 8, so 8 to the second, 8 to the third, 8 to the fourth. This is a geometric series. Actually, in front 7 is also a geometric series, just starting from a different spot, right? So it's a geometric series that starts at 7 and multiplies by 8 every time you go. You have a formula for how to evaluate it. And you will see that the formula simplifies through this. If I instantiate it with the largest, so basically my base is B, and the coefficient in front of it is B minus 1. So that will be the case where the geometric series summation formula simplifies, and it will be just B to the next power minus 1. And this also makes sense, because then this is the 8 to the 5, right, is represented as the smallest 6-digit number in mod 8, I mean base 8, right? The smallest such number has to start with a non-zero, and since I want to do the smallest, I have to fill the other digits with a 0, right? So this is the smallest that uses 6 digits, and this is the largest that can be represented with 5 digits, and it's a good thing that they differ just by 1, right? So the system is efficient. I don't have gaps in it. So this is the general formula. It's b to the k minus 1. It would be nice if it was just b to the k, but it's not, and have boundary conditions. So therefore, you have to be careful with boundary conditions, right? So here's this general fact. And if I squeeze my eyes a little bit, I can rewrite this in this fashion, this inequality, right? Which basically gives me a bound on k, the number of digits I need to represent n. Because if n is the largest number that uses k digits, that conversely, k is how much I need to represent it. So because k is this, so in other words, if I start with n and I ask you a question, the opposite of this question, not what's the largest number that is representable, but I start with a number and I ask you what's the minimum number of digits I need to represent it. Well, this is the smallest integer that satisfies this bound. And the simple equation for smallest integer that satisfies some bound is this, it's a ceiling. That's exactly the definition of the ceiling. It's the smallest integer that is at least what's inside. Okay, so this gives you a closed formula. Okay, like I ask you whatever number in whatever base, how many digits you need, this is the answer. Okay, all right. So another thing I want to cover. I have 13 minutes or so, but hopefully that will be that will suffice. Is modular exponentiation. It's a tool we'll use in a crypto system. Recall the easy but inefficient algorithm for exponentiation. If I want to exponentiate b to the power of x, but now I want to do modular arithmetics, okay? Well, I can keep on recursing, just subtracting, decrementing x, and just multiplying by b, by b, by b, by b with every recursive call, right? But if I need to compute b to the 1 million, okay, this will take 1 million moles, okay? And in cryptographic applications, the exponent is as big as the modulus often. So this might have not 7 digits, but 100 digits. Okay. But recall this fast exp algorithm, right? Which caused people such grief at the homework from recursive algorithm, where I said, okay, you know how to search and you know how to jump from exponentiation to fast exponentiation. Why don't you use this principle to do a fast search on a sorted list? Which admittedly was a bit of a jump. So fast exponentiation works like this. It basically slashed the exponent by half. But if it's an odd, then it cannot quite do that. So it just went into one less, right? So it's x diff 2. And based on this recursive call, it squared it if x was even. And it squared it, but there's a multiply by base one more time if x was odd. That's how it was presented at the time. Now, because I want to do modular arithmetic, so I have to perform all of these mod n. Okay. So not much change, right? So it's only this part really changes from the way this same algorithm was described a few, 2 weeks back or 3. And also I didn't use div and mod notation, but it's the same thing. Okay, now note that I can represent x mod 2, because, okay, if x mod 2 is 0, then I don't multiply by b. If x mod 2 is 1, then I do multiply by b. Well, I can just say you do always multiply by b. It's just that the exponent is x mod 2. Because notice that if x mod 2 is 0, then this b to this is really just 1. So there's no multiplication really happening. And if x mod 2 is 1, then b to x mod 2 is b. So here is a faster, more concise code. I do a recursive call. I square the result and multiply by b x mod 2. It's the same as this code. It's just combined, right? In the x mod 2 equals 0 case, you do this. This line is the same as that line. And if x mod 2 equal 1 case, this thing is the same as this thing. Okay. So here is my code. And now a proof of correctness. Well, this is the same proof I had really, it's the same proof that we did a few slides back. I mean, few weeks back, right? So here it is again in the concise form. That, you know, I would just do the recursive call, because I mean the base case is easy. Fast x x on x is the result of this recursive call squared times this thing. Now, why is it correct? So now, by inductive assumption, this is a smaller argument. So let's assume that this recursive call was correct. That means that it returned this value. This is b to whatever the exponent was, which was x div 2, and correctly computed modu n. And now what I do on the way out, I square it and I multiply by this. So now, as you know, all the modular arithmetic reductions can be postponed, basically, right? Because this is a square of two things computed mod n. So this is the same as just square this thing and then do the modular reduction. And then I will have a multiplication of something mod n times multiplication of something mod n. Well, I can kick the mod n stuff on the way out, right? Like, just do it at the end. At this point, I'm left with b to x div 2 squared, which is the same as b to 2 x div 2, right? Because that's how exponentiation accumulates, right? Exponents got multiplied. And times b to this, but then now that I have b to something times b to something, I just add the exponents. And this thing here is x, right? Just stirred it. This is x, because that's that's the general equation for what does it mean to represent, to, you know, what's the relation between x div something plus x and x mod something. It's that something times x div plus x mod, right? That's the basic constraints that binds the div and mod operations. And by the way, this is exactly the same formula that we used for representing x mod 2, right? So if you go a few slides back and you think of like, how do you represent x mod 2 using this recursive call? It will do exactly this. This will be the recursive call in that algorithm too. Okay, so in some sense, it's a really very similar recursive algorithms. You know, one represents a number base 2, the other one does exponentiation. And if you write them out, like, the reason they work is like kind of one-to-one. It's the same argument. And okay, so okay, so why is this better? Because because how many times you do this, right? Every time you do this recursive call, your integers goes down by a factor of 2. Sorry, here, right? This is the values in a recursive call, in a right? So your initial x and your next x will be twice smaller. So how many times do you do this, right? It's a logarithm base 2, right? Because if you slash, you know, if I ask you how many times do you need to slash x by 2 by 2 by 2 by 2 by 2, log 2x is the answer, right? It's the definition of log 2 of something. So that's how many recursion steps you will do. And what's the cost of each? Here is one multiplication model, and here is another. Moreover, this one is, you know, because this whole thing is just, it tells you whether this is a 0 or a 1. So on average, indeed, you only multiply half the time, right? If your exponent x is a random number. But at most, you do 2 mults. So in the end, you know, all, let's say, computing this takes a logarithm of this, which is 20, right? Because logarithm base 2 of 1,000 is 10, million is 20. And so this whole thing would just take 40 moles at most. And for a random exponent of this size, it would actually take 30 moles, right? So, and so for cryptography, when your modulus is 100 digits, well, what's the logarithm of that? It's 100 times log 2 of 10, which is 3 something, right? So it's, let's say, 300 binary. So 300 binary would mean that this now will become 300 times 2 moles per each recursion, so 600 moles. Okay, so okay, yes, this is significant, but a mult is not a super expensive operation, right? So you have, by the way, mults. What do you think of a mult on a processor? Is a mult of fixed size numbers, right? So a long, which is like 32 bits, or 64, I don't remember, right? Or 16 bits, or 32 bits, or 64 bits, but in any event, they're fixed registers, and you can multiply them. And so these are implemented, well, to the best actual approximation in hardware. But in cryptography, you know, we don't have 64 bits, we have like 300. So you still have to do some more operations, and there is, it's non-trivial how to do that, but yeah, it's sort of roughly, actually, it's not linear, it's semi-quadratic. But still, it's relatively fast, right? So you just have to do, say, 600 of those to do it for like a realistic crypto system. Let's see if, oh, the last thing I have is that I can run this code a little faster. I can write it in place without recursion. So for basically all these codes that I just gave you today, you can say, okay, you know, nice, you have like this super concise recursive algorithm, but in practice, recursive calls are kind of an overhead, right? Like with every procedure call, you have to create some local variables, you create a new frame, you passing things. If you wanted to be really optimal, you would do a computation so-called in place. So you would actually envelop your recursion and implement it with a loop. Okay. In particular, if you wanted to, well, okay. Some hardware actually works by recursion too, but so you might have two versions of these algorithms. One is the one I just showed you, recursive one, but another is in place. The book sometimes has the recursive, sometimes has in place. Let me just give you one example of in place corresponding algorithm. So this fast exponentiation, you could code it like this. Let this be the binary representation of x, right? Which, because if you recall it here, you know, I basically do x div 2, x mod 2, x div 2, x mod 2. This is exactly the binary, as I was saying, right? This algorithm will eventually compute all the bits of x. So let's just do this. I mean, let's just say that we start with a binary representation, okay? Then I could arrange this loop in a very different way. Start with the 1, so start with the base case of the recursion and go the opposite direction, from the highest digit to the least. The recursive algorithm I just gave you went from the least digit to the next, to the next, to the next, because it went in the same direction as the algorithm that represents x mod base 2. But you can go from this side, and if you write out the recursive tree of these calls, then you will see that the base case is 1. And then on the way up, you always square, and you multiply, and you don't do anything if the corresponding bit of x was 0, or you do multiply by b if the corresponding bit was 1. If you stare at the recursive algorithm, that's exactly what it did. It took the initial thing was 1, the base case was 1, and then every time it moved up, it squared, and either multiply by b if the corresponding bit of x, this really is this bit of x at some point, was 1, and if it was 0, then it didn't do any multiplication, it just squared, right? This is the same code, but okay, well, it's not the same code, it's the same algorithm, but just looked somehow backwards from the base case back to the initial condition, and well, it doesn't look the same algorithm, it's kind of just a different way of looking at it, but and if you are told, okay, do fast exponentiation, you can do either one, whichever you find more convenient. It's good to understand that they are really the same, that they're based on, it's the different way of looking at those two different ways of looking at the same algorithm. Okay, so thanks. Sorry for overstaying, which is a few minutes late. Let's move to questions. Hello. Do you guys have some questions about the stuff?
So most of the stuff is on the next homework?
Yes. Yeah, I haven't released the next homework, but I will do so right now. And one more thing that I still I think that I will need to make like an online lecture at some point, because I'm not sure that I will have enough time in the remainder of the class for the combinatorics.
I have a question on number 4 for homework. It is homework 6. Yeah, homework 6, problem 4, the modular arithmetics. So a quick question about that, because like when I was making the table, so then it's asking us to write out a 7 by 7 multiplication table with the modular multiplication, like with a multiplication modulo 7. Because I went from 0 all the way to 6 on one way across, and 0 to 6 one way down. So then I multiplied whatever the two columns give, like, but then and then like we have to answer all these questions. Like let's say if there is a 1 in every row, but then like let's say if we were to take the mod. But what this is asking us is it's whatever's a multiplied by b mod 7 to the power of 3. Am I reading that correctly?
A
multiplied by b mod
not to the power of 3? I don't think so.
Yeah, what does that power of 3 stand for? Because I can't really tell. Oh, okay, I see. We did this in class for multiplication. Okay, never mind. Sorry. It just looked like a multiplication sign because I didn't see that there was a subscript or a superscript in referring to. Yeah.
Okay.
I see. Sorry.
Okay. Any questions on this stuff?
Yeah, so does you just moved off the slide, but does the number have to be represented in binary for the final algorithm? Yeah. Is it necessary for it to be represented in base 2?
Yes. Yes. So this code assumes that these are the bits of x, because this is because like if you envelop here, these every time you do the recursive call, the previous x becomes x div 2, and this thing is whatever this x was mod 2. Well, so this is exactly this algorithm. If B is 2, this is x, okay, and n is x, okay? N is x, B is 2. So this is x mod 2, and this is, you run recursively on x div 2. So these things were every time you move x to x div 2, x div 2, x div 2, you spit out whatever x was mod 2. And it turns out that this spitting out is actually spits out the representation of base 2 of your x, right? So this is the same thing is happening in this algorithm right here. You're running recursively on x div 2, and you're spitting out, quote unquote, x mod 2. So these things will be bits of x. So the going up algorithm just says, okay, so let's call these bits of x, x0, x1, x2, all the way to like xn for some n. And let's start at the bottom, the end of the recursive call. Then I will have this. You know, I can write it on. If you want to stay a little bit, then I can show it to you on a piece of paper.
Yeah, I think I understand it more now, that especially now I'm looking at the base or recursive cases themselves, much more simpler inside a binary representation, since it's only 0 and 1 that we have to care about.
Mm-hmm.
Yeah, I think I'm good. Thank you.
Okay, sure. Welcome. So somebody asked on the chat if I could go over the inverse computing multiplicative inverses. Somebody said, I think that to go over multiplicative inverses again. So let's do that. It's this stuff here. Okay. So what did you want to ask about it? Okay. So this just goes over, yeah. Well, okay. So here I was arguing. Oh, somebody asked on the chat if we have proofs in the next test on this material. No, I don't think so. Yeah. I think not really, but maybe I come up with something. No, I'm joking. I don't know. No, it tends to be more no, because you know what this is. I mean, you know, basically the proofs would be like. I mean, maybe there's at some point like something like, you know, in the end, sort of to understand like why this algorithm is correct is to understand the proof of it. On the other hand, this is not a great test question, right? Because you just look at the book and you just copy the proof. So what that did test? If it's an open book test, it makes no sense to ask that. Yeah, no, so the test will be more like, okay, use it for something. Okay. So, okay, so coming back to the slide, so if I so extended Euclidean algorithm for n and x inputs gives me this s and t coefficients, and the t coefficient is the multiplicative inverse of x mod n. And why is that? this is the explanation. Okay. If I start back, sort of backwards, I say, okay, what is the multiplicative inverse? Is some integer b such that xb is 1 mod n. But if that is so, then this relation has to hold. So b is bound by this relation. But this is precisely this relation. Okay. So if I just call this guy b and call this guy minus m, then this relation and this are the same relation. So my b here, in other words, the multiplicative inverse of x was hiding in plain sight. It was just this value, t. Okay? And you can verify also, if you reduce mod n, both sides, then mod n, some multiple of n vanishes, and all that remains is t times x. And on the right-hand side, well, 1 doesn't vanish. So this equation basically implies that tx is 1 mod n. And that means that t is a multiplicative inverse of x mod n. Okay. All right. Okay, so I'll be cooking up some next homework, and maybe I will post another lecture because I'm a little bit I wanted to squeeze a little more stuff and just went a little slower. I'm not really sure. Okay, so thank you so much, and see you next time.